Well, it's getting there. All right. So we talked about the specific heat yesterday. Not yesterday, sorry, the last class, right? Okay. And our conversation ended with this. Now, I want to remind you that specific heat refers to the amount of heat that you need to deliver to a substance to increase its temperature, by 1 degree Celsius, okay? And we're talking about 1 gram of the substance. So for instance, to increase the temperature of water, 1 gram of water, by 1 degree Celsius, you need to apply 4.184 joules. That's the specific heat of water. And I want to remind you that specific heat is measured either in calories per gram per degree Celsius or joules per gram per degree Celsius. Okay, good so far? As a reminder. Now, we're also going to be, so there will be a couple of questions on that lecture assessment that will address the calculations of the heat. For instance, I can ask, here's I have some water, certain mass, here's the specific heat of water, here's the temperature difference, how much energy you need to deliver. Does that make sense? To get from 25 degrees Celsius to, 75 degrees Celsius. All numbers are going to be very straightforward. You're still allowed to use calculators. Am I clear? You should be able to also produce, for instance, I ask you, specific heat of water is such and such. We delivered so much heat to 50 grams of water. What's the temperature change? So basically, you need to be very comfortable with that equation on the screen. Okay? Now, another heat-related problem that I want to talk about is change. Question? Say it again? Yes. So, heat equals mass multiplied by change of temperature multiplied by specific heat. So, that's the guide, okay, how you do it. And based on what you know, based on what you don't know, you change the order of events one after another. Okay? So for instance, okay, let's do one example because I'm really a bit concerned about this. So we have heat, okay, equals mass multiplied by change of temperature multiplied by specific heat. Okay, can you see that formula? Now, if we need to know heat, what do we need to do? And I give you mass, change of temperature, and specific heat. You simply multiply these three things. Am I clear? Now, if I tell you, here's the mass, here's the specific heat, here's the total heat. Find me delta T, change in temperature. What you going to do? Go ahead.
Divide by both sides.
So you divide heat. Okay, you divide heat.
No, you divide temperature change by both sides because you got to try to get that by itself.
Yeah, but in this case, you need to divide both sides by mass and specific heat. Then you isolate temperature. Does that make sense?
Oh, yeah.
Got it? So use the same approach for whatever I ask you to find. Does that make sense?
Say that again, divide both
So-
sides by...
So for instance, here in this example that I'm showing you on the screen, you need to find change in temperature.
Yeah.
So you need to isolate change in temperature on one side of the equation. So you divide each side by mass and specific heat. they get cancelled on the right side, but they appear in the denominator on the left side. Okay? Make sense? And always check that the units are correct.
So are you multiplying mass and specific heat and then dividing it by the solution, or are you just taking them individually?
It doesn't matter.
Okay.
It doesn't matter. The order doesn't matter. You can multiply mass and specific heat on the right side and then use this product and divide heat by the product of that multiplication, but that's purely math. The order of operations here doesn't matter. Okay? That make sense? Heat is 1,000. Mass is 10. Specific heat is 10. What's the temperature change? So heat is 1,000. Mass is 10. Specific heat is 10. What's the temperature change? No. Wait, yes, 10. Good. I mixed up. 100, yes. So you divide 1,000 by 10. You divide 100 by another 10. And get 10. Okay? Does that make sense? Now we're going to actually look at similar problems when we're going to be talking about the change of state. So change of physical state is when matter goes from, say, liquid to solid, or solid to liquid, from liquid to gas, or from gas to liquid. So we have some specific terms for this. Well, melting is from solid to liquid. There's nothing new. Freezing is from liquid to solid. Does that make sense? So the point, the temperature point at which melting, or freezing for that matter, occurs, we call it a melting or a freezing point. For instance, for water, this point will be 0 degrees Celsius. So at 0 degrees Celsius, what's going to happen to the liquid water if you keep cooling it down? It's going to freeze. What's going to happen to the ice at 0 degrees Celsius if you keep heating it up? It's going to melt. Okay? Now you have to understand that these processes are reversible. So if you melted something, you can freeze it, and vice versa. And perhaps more important is to understand that the heat of fusion is the same whether we're talking about melting or freezing of a substance. Now let's define the heat of fusion. So it's the amount of heat that is released when 1 gram of substance is freezed, or the amount of heat that is required to melt 1 gram of solid substance. For instance, the heat of fusion for water is 334 joules per gram. Does that make sense? Just that's the number. I gave you a number. It's 334 joules per gram. What does that mean? It means that in order to take 1 gram of ice and make it 1 gram of liquid water, you need to apply 334 joules of energy to that 1 gram of ice. Does that make sense? Now let me ask you this. How much energy do you need to melt not 1 gram, but 1 kilogram of ice? How many grams are in kilogram? 1,000. So if to melt 1 gram of ice, you need 334 joules. How, huh? 334 to melt 1,000, huh? You multiply it by 1,000. Does that make sense? So that's one thing. Basically, in order to find how much energy you need to melt certain amount of solid, you need to multiply the mass of the solid by the heat of fusion. And that's it. Mass multiplied by the heat of fusion. Does that make sense? Now, let's say I tell you the different problem. I have 10 grams of water. 10 grams of water freeze. How much energy is released? Yeah, 334 joules times 10. Because that is the amount of heat that will be released when liquid water turns into ice. Does that make sense to you? Now, what's really important to understand is that the heat that is released during freezing is the same that is heat released during melting. So when 1 gram of ice goes from solid to liquid, it requires 334 grams. When it goes back from liquid to solid, it will release 334 joules. I'm sorry, not grams, joules. Does it make sense? Everybody understands? Okay. So this is a formal guide. Let's do that. Okay. So basically, again, heat of fusion is an example of a conversion factor. For instance, for water, that conversion factor will be 334 joules per 1 gram. Or vice versa. 1 gram per 334 joules. Depends on what you're going to try to find. Does that make sense to you? Now, second concept. Transition from liquid to vapors, from liquid to gas. Evaporation is conversion from liquid to gas. That's the you need to give molecules on the surface of water sufficient amount of energy so they will fly away. Does that make sense? And that explains why water at the room temperature evaporates much slower than the water on the hot kitchen stove. Because when you put water on the hot kitchen stove, energy is delivered to the molecules and molecules are basically flying away. Got it? Condensation is bad. So what you saw, like what you can see sometimes after the rain, when during the night the air cools down, the water vapors that are in the air, they condense in a tiny little droplets that form fog. That's condensation. Does that make sense? Let me ask you the following. The heat of evaporation and the heat of condensation, how do they relate to each other? Heat that is required to evaporate 1 gram of water and heat that is released when 1 gram of water is condensed. They are the same. Are we clear about that? Does that make sense? So boiling, the interesting thing about boiling, in chemistry we don't really work with ice that much, but we work a lot with boiling substances, right? One thing, imagine that you have water at the room temperature in the beaker right here. And you start heating it up. In the meantime, you have a thermometer that measures the temperature of water in the beaker. As you're heating it up, what will your thermometer show? Increase in temperature, yeah. Now, at which temperature water boils at this elevation? 100 degrees Celsius, yeah. So it reaches 100 degrees Celsius, right? Thermometer reaches 100 degrees Celsius. Water starts to boil. You keep heating water. What's going to happen to the thermometer? You think it's going to go up? The interesting thing is that at the melting or freezing point, boiling or condensation point, during the process, for instance, of evaporation/condensation, during boiling, there is no change in temperature because all energy that is delivered to the liquid, to water here, all that energy will be used to evaporate water, to, send molecules off into the air. Does that make sense? There will be no energy used to actually increase the temperature. Are we clear? That makes sense. So condensation, evaporation is pretty straightforward. For some substances at the normal atmospheric pressure, they miss the water part and they go directly from solid to vapor. This is called sublimation. And deposition is the opposite process. Okay, when you have gas particles, they become solid directly. Anyone ever worked with the dry ice? Dry ice is a solid form of carbon dioxide. If you ever tried to throw dry ice in the sink, or better yet, toilet, that's a hood. Because dry ice, first of all, dry ice doesn't melt. It goes through sublimation and becomes gas, okay? As it becomes gas, it's still very, very cold, so it forms a lot of fog. And if you be careful, but buy some dry ice, come home, throw it in the toilet. Not a lot of it, not like 5 pounds, maybe a couple of scoops, and you're going to have a massive amount of fog coming out of your toilet. That is the best thing. Kids can do that like for hours. The only thing to be aware of, you have to be careful because if you freeze the water in the toilet, which is possible, that's going to be a bummer. You may need a new toilet. So, bit by bit, okay? We had situations when we threw like 5 pounds of dry ice in the sink, in the lab, and the water in the sink totally froze. Just for like several feet, there was like a chunk of ice. But it was cool, just wait. So that is sublimation. Another example of sublimation, if you take iodine, solid iodine, and you heat it up, it goes directly from crystals to vapors. It doesn't go to the liquid stage. That makes sense? So sublimation allows us to prepare the freeze-dried foods when we cool things down and basically remove significant amount of water. Now, we already mentioned the heat of fusion. This is the heat of vaporization. So heat of vaporization is the amount of heat that you need to convert 1 gram of liquid to gas, or the amount of heat that will be released when 1 gram of gas condenses back into the liquid. As we mentioned, the heat of vaporization and the heat of condensation for the same substance are the same. Are we clear? So that's the heat of vaporization for water. So in order to convert 1 gram of liquid water into gas, you need 2,260 joules of energy for 1 gram. Does that make sense? Now, don't worry about these numbers. Don't memorize the specific heats, the heats of vaporization or the heats of fusion. I will give you those numbers in the problems. You need to be able to calculate. Okay. For instance, I tell you have 40 grams of water. How much energy you need to convert 40 grams of water into vapors? Say it's boiling. Okay. So what you need to do? Go ahead. You need to take which number? Yeah. No. Here, you multiply, because think about this. Think about the heat of fusion or heat of evaporation. It's the price. That's the price you have to pay to go from solid to liquid, or as in case of heat of vaporization, from liquid to gas. Does that make sense? So the price tag here is 20 to 60 per gram. How much do you have to pay for 40 grams? How much? 40 times more. I would be satisfied with the answer 40 times more. Is that clear? Does that make sense to you? You got it? Think about it as the price that you have to pay to convert from one state to another. Make sense? Good? Okay. Now, all the temperature transitions of a substance can be described using the heating curve. And this is the typical heating curve. You can see that such curve has several, shall I say, parts. So you see the incline diagonal lines. For instance, this diagonal line here, it describes the change of temperature of liquid water from 0 to 100 degrees Celsius. And this horizontal line describes the change of state. Are we clear? So if you start with very cold ice and you heat it up, when ice itself heats up in this part, does it change the state? No. Let me erase this all. So here, does ice change the state? No. What happens here? It melts. It changes its physical state into water. Water here, does it change its physical state? No, it heats up. Here it does what? Evaporates. Boils and evaporates. And here you have gas. Okay? And you can heat up gas and it doesn't change its physical state. It remains gas. Does that make sense to you? Same idea is with cooling curve. Okay? So with cooling curve, here's what you see. You have steam, you cool it down. As steam cools down until it reaches 100 degrees Celsius, does it change its state? When it reaches 100 degrees Celsius, what happens to it? Changes. It condenses into liquid, into water. When water cools down, it remains water until it starts to freeze. And then when it freezes, it becomes ice, and you can cool ice down all you want. it will remain ice. Does that make sense? So horizontal lines, they represent essentially change of state. Diagonal lines represent either heating or cooling. Am I clear? Now, sort of a culmination of a problem. There will be one or two, I don't remember from top of my head, on the exam. The problem that you will have to do is to calculate the total heat. Let me explain what I mean. Let's say I tell you, you have water. Okay, we can do it together. Actually, I will try to do the following. Okay. Let's go blank. Okay. See that? So we have water. Sorry, I'm going to change the color now. Water. Temperature. Let's take 50 degrees Celsius, okay? Are you with me? I give you a generic, absolutely like generic problem, okay? So that's the temperature that you start with. That's your starting temperature, 50 degrees Celsius. I give you the mass, which is going to be 20 grams. Okay? And then I tell you that I want to know the amount of heat that you need to deliver to turn all this water into the vapor, into the gas. How would you approach it? What do you need to do first? It's 50 degrees Celsius. What do you need to do first? You don't need to multiply. Yes?
This not the one that's H equals M. This not that.
Boring. What do you need to do first with this water? You need to heat it up. No offense. I want you to understand what we're doing. Forget about the math. Math will come. Okay, math will come later. You have 50 degrees Celsius water. To evaporate it, what do you need to do first? Heat it. To what point? Boiling. And then you need to boil it until it all evaporates. So you've got two distinct processes. Heating it up. Does that make sense? And boiling. So you've got to use two heats. Now, first equation will be what? Mass. You just said mass.
And the temperature change time.
Which is what?
100?
Change. 50. 100 minus 50. Does that make sense?
Oh, yeah.
Okay, so temperature change multiplied by what? Excellent. Why I called it H2, I don't know. Let's just keep calling it H2, okay? That was accident. Do you understand what we just did here? No? You just told me. You just told me the whole thing. So what does this heat tell us? It's the amount of heat that you need to do what? To get it to? No, to the boiling point. That's the amount of heat that you need to get the water to the boiling point. Does that make sense to you? You sure? Okay. Now let me go forward for a second. So this is the part of the heating curve. Can you see it? This diagonal line, what does it represent? Heating up the water. Okay. This horizontal line, what does it represent? Boiling, evaporation. That makes sense? So I have two distinct processes. So this temperature H2 to which line does it pertain? Diagonal line. That's you heating up the water to boiling point. Does that make sense? Now, what's going to be your next heat? What do you need to do? How do you calculate the amount of heat that you need to evaporate boiling water? Hold on. You need heat of vaporization, right? Heat of vaporization, and you multiply it by what?
By the grams?
Yeah, by the grams, by the mass. Let's go over it one more time. Yes?
So what is the specific heat? Like, that'd be 2050, but what is it times the specific heat?
Specific heat is the number that how much energy you need to heat up 1 gram of water
So the 100?
by 1 degree Celsius. No. So specific heat for water is going to be 4.184 joules per gram per Celsius. Yeah, you will get all the numbers. Sorry, question.
I'm trying to
Okay. Okay. So we're going to talk about, so that's basically the whole combined heat calculation is shown in this problem. We can try to just go through the slides. I tried to do it all together. Do you want to do that? Just going to work on that, and then we're going to do the combined heat calculations during the lab, all right? So you have 15 grams of ethanol, which is liquid, at 25 Celsius to heat to gas, and the boiling point for ethanol is 78. You provide it with a specific heat and the heat of vaporization. Okay? So your answer should be how many kilojoules, how many thousands of joules you need to use, make sense, to convert this 15 grams of ethanol to vapors. Yes, go ahead.
So it says calculate the total heat in joules.
In joules. Well, I will be specific. I can tell you in all problems in the exam it will be joules. All of it is going to be joules. No kilos, nothing like that. Okay? Now, first, you need to figure out what are the two processes that you're looking at here. One is heating up ethanol from 25 to 78. Does that make sense? You go from room temperature to boiling point. Second process is actual evaporation at 78 degrees Celsius. Okay? And then you need to calculate heats that are required, the amount of energy that is required for each of these processes. So first, you need to calculate how much heat you need to get the amount of heat to get ethanol to its boiling point. Remember this equation that we wrote, H equals M multiplied by the change in temperature multiplied by the specific heat. Remember that. What's the M? I mean, like physically, 15 grams. What's the change in temperature? 78 is the one that you need. 25 is the one that you have. Where did I take 53?
I was trying to write the formula down. I didn't even hear you.
Oh, the formula is right here.
I know I wrote it.
Okay, so what I'm saying is mass is 15 grams, it's given. Change in temperature is 53 degrees Celsius. Because it's 78 minus 25. And the specific heat is whatever is given, 2.46 joules per gram per Celsius. This is the result. This is how much heat you need to get 15 grams of ethanol from 25 to 78 degrees Celsius. Okay, next one. You need to calculate how much heat you need to evaporate. So, in this case, the heat will be mass multiplied by the heat of evaporation. That makes sense? The mass is 15 grams. The heat of evaporation is provided being 841 joules per gram. So that's the heat that you need to evaporate that ethanol. Put them together. This is your answer. Does that make sense? The last step is questionable. What do we do at the bottom here? Is this unclear? Yes.
I have a question about significant figures.
Yes.
So, because we're both multiplying and adding, do we just follow?
You multiply first.
So we take multiplication as the precedent?
You multiply first. So you multiply here, okay, in this equation. How many significant figures are you going to get in your answer? So you have 3, 3, 3, so your answer should contain 3 significant figures. Okay? That's your number 1. Number 2. 3 significant figures, 3 significant figures. So your answer should contain 3 significant figures. Okay? Now when you add 2 numbers, how do you know how many decimal points you should have? The least number of decimal points. Both these numbers, 12,600 and 1960, they have no decimal points. So you just add them. You don't worry about anything else. Does that make sense? What is confusing?
I'm just, the last part you said there's no decimal point, so we just need to add it in.
If there would be any decimal points, it's going back to our discussion of significant figures. When you do addition or subtraction, the number of decimal places that you need in your result corresponds to the least number of decimal places in numbers that you add or subtract. Okay. Here they don't have any decimal places, though. It's fine. Just don't do anything. Okay? We're going to do that not that problem, but similar problem during the lab today. Okay? Are we clear? We're going to do it together, and I really want you to write it down. Now, this concludes the chapter on which you will be assessed on Wednesday. We're going to start the next one, which is going to be, let's say, more chemical. Now, chemistry, being an extremely elegant science, a logical science, requires a good deal of memorization. And I will try to feed you not the entire elephant, but bit by bit. Okay? So absolutely for each assessment you will have to memorize certain things. But I will try not to overdo that memorization part. For instance, when we talk about substances, elements, compounds, you will need to know the names, you will need to know the the letters, the symbols, it will be sort of restricted. I will not ask you to memorize the entire periodic table. In no circumstance. So, let's talk about what are elements, what are compounds. So, elements are pure substances. Okay? Examples would be hydrogen, oxygen, carbon, iron, aluminum. All are pure substances. Very rarely we meet elements in our life. Okay? Usually we either work with compounds or we work with mixtures. Are we clear? The distinctive feature of any element, it cannot be broken down into anything simpler. So hydrogen is hydrogen. You cannot make it anything else than hydrogen chemically. It's always going to be hydrogen. Hydrogen atom is hydrogen atom. Now, in your textbook, elements are on the, what they call it, inside front cover. Okay. So, these are the names for the elements. I always say that there is a special place in hell for taxonomists, people who give names. There is no special taxonomy in chemistry, so scientists that give names to elements, they give those names based on the whim. Okay? So, for instance, oxygen received its name because it can produce oxides that can then turn into acids. Okay, it can oxidate things. Substances can burn in oxygen. Hydrogen was given its name, hydrogen, because it can generate water. Okay? So, names sometimes, like uranium, named after the planet. Okay? Palladium, which is not on the list, I suppose, was named after the asteroid. California was named after the U.S. state. Okay? Chlorine was named after the color. It's a yellowish, greenish gas. Ruthenium element was named after the country, Russia. So names come in all tastes, and there is no logical way to know what, why the certain element is given a certain name. Does that make sense? What you can do, what you can sort of make associations about, are symbols and names. So for instance, for uranium, it's U. Don't ask me why it's not UR. I have no idea. For titanium, it's Ti. For chlorine, it's Cl. For many of them, you will see that symbols actually reflect the name. Does that make sense? Like in the entire list here, there's at least some reason, okay? For instance, you may ask, okay, curium, why it's Cm and not Cu? Because Cu was taken by copper, okay? So we can't name it copper. Copernicium, why we can't name it Co? Because Co is taken by cobalt. Does that make sense? So that will come. You will remember the symbols for basic elements. You will not notice how fast you will remember those. We have one-letter symbols for some of them. Okay? Carbon, hydrogen, fluorine, phosphorus, nitrogen, so on and so forth. We have a bunch of two-letter symbols. Now, I'm not really particular about it, to be honest. I've understood why any chemistry teachers are. But the symbols for the elements always start with a capital letter. So this is correct for copper, and this is not. Does that make sense? Always starts with a capital letter. The names of the elements do not start with capital letter. Am I clear? So if you say we take copper, copper is just normal word. It's not a personal name. We take iron, iron is a normal word. It's not a personal name. You clear? Now this is a bunch of names in which I want to point your attention to some sort of standouts. Copper, which by all means should be CO, but carries the symbol Cu, because in Latin its name is cuprum. Okay. Lead is plumbum, so it gives Pb for lead. Iron is ferrum, which gives Fe for iron. Gold is aurum, which gives Au for gold. Potassium is calcium, which gives K for potassium. Silver is argentum, so Ag for silver. Sodium is natrium, and tin is stannum, which determines the sign. So you can see that for sodium it's Na from natrium, and for tin it's Sn. One that is not shown, you may have heard antimony. The element antimony has Sb, which comes from Latin stebium. Chances are, in this course, you're not going to encounter antimony or tin. Maybe mercury, which is hydroargyrum, and therefore the symbol for it is Hg. Few things. Do not memorize this table. I will tell you exactly in the study guide which symbols to remember. We're going to take it bit by bit. Okay? Am I clear? Whitney, question?
The test that we have on Wednesdays over chapter 2 or 2?
Just 2. Just the one that we finished. Like the one that we finished the block.
Right.
It said, this is not for the test. Don't worry about it. Okay? Now, that kind of shows you a lot of it is derived from Latin names. Later, the elements, the later discovered elements named after famous scientists, cities, states, like Californium or Americium, okay, or Copernicium, stuff like that. Now, perhaps the most important element for us in this course, since you ultimately will transition into biological and biomedical sciences, is carbon. Okay? So carbon can exist in various forms, and this is something to be aware of. Forms that are called allotropic modifications. Let me explain. Coal, is that a carbon? Yeah, it's a carbon. Graphite in your pencils, is that a carbon? Yes. Diamond in jewelry, is that a carbon? Yes. So they're all chemically similar. But atoms in each of these 3 forms are organized differently. For instance, in coal, they aren't organized in any particular, particularly systemic structure. Does that make sense? Now look at organization of atoms in carbon. It's very intricate. It's 3D. Each carbon is connected to, as far as I remember, 4 others. So they create really strong, hard to break crystal structure. Now, if you would look at graphite, I don't know if you can notice that. They organized in layers. Can you see the layers? When you write these layers, basically like tiny little scales laid down on paper, this is why you can see the writing. Does that make sense? Now, if you would look, there is another form of carbon called fullerenes. For instance, the Buckminster fullerene looks like a soccer ball. They have some really interesting chemical and physical properties. But it's all different forms of one single element, carbon. Does that make sense? Now, I'm desperately trying to think about any other example of allotropic modifications of an element. The only one that I can think of on top of my head is phosphorus. You may have heard about red phosphorus, white phosphorus, black phosphorus. For instance, white phosphorus is extremely reactive and can catch fire to open air. If you expose it to open air, it just catch fire. Does that make sense? Red and black phosphorus, they're much more stable. But they're all phosphorus. Same element. Now, elements are organized in the periodic table. So, periodic table isn't just a random set of squares with elements placed there by a certain whim of a scientist. It was first suggested, the organization of periodic table was first suggested by a Russian chemist, one of the greatest Russian scientists, Dmitry Mendeleev. The legend has it that he actually saw it in his dream. And he suggested to organize elements based on the number of protons, the charge of the nucleus. And we will see that it actually worked. Okay? Now, Mendeleev's discovery was so important, really, that he managed to predict the properties of certain elements, and he managed to predict the discovery of certain elements. Basically, is that here there should be an element with such and such properties, okay? And later scientists discovered an element with such and such properties. Does that make sense? Because elements in the periodic table are grouped according to a certain order. They're grouped in the periods and groups based on the properties. Now, if we go back to the periodic table, those of you who have a book can open the periodic table. It should be somewhere there. So, the columns are groups. The lines are periods. Does that make sense? Now there is a ferocious fight over how to name the groups. I belong to the old school, but I will use the numbering that is more modern as well. You will not have to choose between the two camps, okay? The old school and the new school. Basically, what the old school says. So if you would look at the naming of the groups, can you see 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so forth? Just the Arabic numbers. That's the new school. New school says that there are 18 groups. The old school says that there are 8 groups. So 1, 2, 3, 4, 5, 6, 7, 8. Okay? These ones are called transitional elements. And they're called sometimes transitional groups. These ones are called main groups. Now, it's all taxonomy. It shouldn't concern you. What should concern you is why certain elements belong to a certain group, or why certain elements belong to a certain period. Does that make sense? And we're going to reveal why that's so. Okay? So this is the explanation of the system that I was talking about. So group numbers 1 through 8 with the letter A, 1A, 2A, 3A, and so on and so forth. That's the main groups, the representative elements. Groups 3B to 2B, 1B, 2B are transition elements. Alternative system gets rid of the letters overall and just assigns the numbers 1 through 18. Okay? In the United States, this system is used the most, 1 through 18. Okay? Yes.
But everywhere else in the world.
It depends, really depends on the taste. Like, if you would have a 70-year-old chemist who was brought up mostly in Europe, they will be using 1A, 2A, 3A. But here's the deal. That's naming. You know what I'm talking about? That's not essential. That doesn't change why certain elements in the certain groups. Am I clear? And I would care more, not more, exclusively of why they are in a certain group. Why sodium, potassium, lithium, cesium, francium all are in the first group. Why all noble gases are in the last group. Why is that? And that's what we will try to answer. Am I clear? So, that's the period, and that's the group. Okay? Does that make sense? Now, some groups carry specific names. Okay? And for the chemistry education, it's important to know them. The first group is called alkali metals. What's alkaline? Less acidic. Well, it's base. Okay, very, very basic solution. Very high pH. So alkaline metals or alkali metals can form really, really strong bases. Does that make sense? This is why. Actually, the word alkali is an Arabic word that refers to the chemical, the base. Now, alkaline earth metals is the group number 2. They also can form bases, but not as strong as alkaline metals. So far, does that make sense? Now, this huge chunk of elements in the center are called transition elements, sometimes transition metals. If you would look at the periodic table in your textbooks or slides, or I can show it to you here, you may notice that among these metals are very many that you may have heard about, like chromium, manganese, Cr, Mn, manganese, molybdenum, Mo, zirconium, Zr, titanium, Ti. Okay? So what makes those elements transitional? why we call this part of the table transition elements. It turns out that in some conditions they behave like metals. Metals that we used to, okay? Like sodium, like calcium. And in some other conditions, they behave like nonmetals. Sulfur, phosphorus, nitrogen. Does that make sense? Now, last two groups in the periodic table, the group 17 and group 18. 17 group is called halogens. The word halogen comes from Latin, which means forming salts. Salt. Like salt. Like salt. Like sodium chloride. Does that make sense? Like table salt. And the last group, the 18th group, are noble gases. They're called noble gases because they do not react with anything. Well, under normal circumstances. Okay? You can buy noble gas in Party City. It's called helium. If you haven't done so, buy, inhale, and speak. That's going to be really, really funny. Now, these groups, 13 to 16, they don't have any common names. Like, not really. So, that's alkali metals. So, lithium, potassium, sodium, rubidium, and cesium. Halogens is 17th group. Okay, chlorine, bromine, iodine. Now, here's the first thing about this distribution. Look at the periodic table. That's our first glimpse into how periodic table groups elements based on the properties. Alkali metals, I just told you, what do they form very efficiently? Bases, very strong bases. Huh? Very strong bases on the left side, right there on the left side. Halogens on the right side. If left side forms bases, what would right side form? Acids. They form really strong acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid are very strong acids. Does that make sense? So they kind of opposite. The halogens form acids. Not just acids, strong acids. Alkali metals form bases. Now, general rule, metals, non-metals. Can you define a metal?
Brittle.
Brittle, okay. What else? One of the most important features of metals. They're pure, they are shiny. They're shiny. Okay. Now, do they have to be solid? That's a tricky one. Is mercury a metal? Yes, it is. Mercury is a metal. Just liquid metal at room temperature. Okay, but it's a metal. So, metals in the periodic table are the blue ones. Okay. Non-metals are the yellow ones. So basically all gases, one liquid, okay, and some solids. These elements are called metalloids because they can behave like metals, but they also can behave like non-metals. Does that make sense to you? So these are physical characteristics of metals and non-metals. So metals, shiny. Most of them are brittle, you're right. Many of them are malleable. And that's important, they all conduct heat and electricity. Are we clear? Non-metals, not shiny, poor conductors of heat or electricity. Metalloids, depends. So for instance, in this list of metalloids, you can see the element called germanium, okay? And there is a non-metal, selenium. So germanium is really shiny. I work with that. Okay, it's really shiny. But what's important about metalloids, they're really poor conductors of they're not terrible conductors of electricity and heat, but they're not as good as metals. So all these metalloids can be used as semiconductors. Now, this brings us to the solid state physics, which I don't want to talk about. Basically, the idea, let me put it this way. If you see a wire like this wire is made of metal. That makes sense? If you see an insulator, have you seen insulators? The power lines. Huh? Ceramic. Ceramics is non-metals. Okay? Can be carbon, nitrogen, boron, composites, stuff like that, but non-metals. Okay? And if you pull out your phone is full of semiconductors. So that's germanium, that's silicon. Silicon Valley is named Silicon Valley because of all the computer industry that is based there, and the entire computer industry is based on the semiconductors. So far. That makes sense? Now, you will need to know the characteristics of metals versus metalloids versus non-metals. Okay? You don't need to know the numbers like this. Okay? No point in this. Does that make sense? By the way, in terms of the melting points, generally speaking, metals have higher melting points than non-metals. So chromium, cadmium, cobalt, nickel, molybdenum, sodium, potassium, they have hundreds degrees Celsius melting point. Does that make sense? A bunch of non-metals are gases, so they have really low melting points. Am I clear? There are exceptions. For instance, mercury has a melting point of negative 39 Celsius. Gallium, that's one of the jokes that some chemists play. Gallium has a melting point of 25 degrees Celsius. Okay? I mean, it's really, really expensive. But if you add gallium to certain alloys, it will give those alloys fairly low melting points. There's a alloy called the Woods alloy, which has a melting point something like 39 Celsius. And there is a trick that some chemists play, the practical joke, when they invite someone over for a tea, and they give them a cup of tea and a spoon, and the person starts to mix the tea, and the spoon disappears because it melts into the tea. It's Woods alloy. It's pretty cool. So there are exceptions, but generally speaking, metals have high melting points, non-metals low. Okay? Does that make sense? So we're going to wrap up this particular portion